Let's take a look at the exploitation of a 64-bit binary here with format string exploit. So in this video, we're going to cover essentially different ways to exploit format string. And in particular, we're going to go over a write what where primitive, which ultimately solved the challenge. So this is the challenge binary. Let's go ahead and load it into IDA to see what's happening. Actually, before we do this, we can actually run the file Ubuntu. So that's what I'll do now. So here we can see the binary. Before we run it, we can always run checksec to see what kind of protections are enabled in this binary. And keep in mind that checksec is a package that's automatically built and installed whenever you install PwnTools Python package. I'm just going to run checksec on Queen's Gambit. And okay, so after a while, we see that a lot of protections are missing. In particular, there's no pi. Pi is position independent executable. It essentially determines where the text of the program is actually going to be loaded into the memory whenever we run it. In this case, there's no pi, so the base of this executable will always be at hex 400,000. So we will not need a leak to determine addresses within the binary. Another protection that's missing is stack. There's no canary found. But of course, NX is enabled, so if there is a buffer overflow, then we can't simply load shellcode. Although this is a protection that's pretty standard in most binaries, even most vulnerable binaries that you'll see in CTS. Okay, so let's look at the binary in IDA. All right. So here's the entry point. Let's go to main. So here's main. Actually, let's run the binary first. Okay, so when we run it, we can see there's a nice banner printed out here. Chess puzzles to train the brain, become a grandmaster. And we're given three options. We can play, we can try to access the chess server, or we can quit. So let's look at play first. So we enter the name. Okay, we can just put anything here. And then we're given a puzzle. And we have to choose the best move. So just in this case here, it looks like here's the white king, here's our rook. If we move rook to a1, then this will be checkmate. Okay. So let's try rook to a1, and we get congratulations, admin, your answer was correct. This was the name that we entered, and your winning move was, and then we have what we entered as the move. Here's puzzle 2. Given the same, or we're given a puzzle just as before. We have to pick the best move. So again, looking at this, here's the king. Here's our queen, and if we move this to here, looks like this is a pretty easy checkmate as well. So that's queen to g7, and that's correct. So again, we get a similar message here, and then our winning move. Okay, so now we have puzzle 3, beat bull over Tron. Okay, and here we are actually in check right now by the black queen, and we have to figure out which position is best to move to. And I'm not too sure about this one. Let's see, so here we have black pawns here, we have a pawn here, and a bishop, black pawn. So it's not too clear where to move. Let's just say king to d2. Okay, so apparently that was right. We get congratulations. That was the final puzzle. We get the winning move, and looks like we won, but the program just exited. Okay, so not very interesting, I guess. Doesn't give us access if we get everything right. So let's look at what happens if we try to do 2. Okay, unauthorized has been disabled, whatever, and of course, into 3 we just quit. So let's look at the program in IDA now. Here we can clearly see what's happening. There's a banner being printed here, and we print the menu. We get the option here, and we scan F. So of course we can do our usual checks for buffer overflow here for S. S is at RBP minus x88, so pretty far up the stack. And it looks like everything is implemented correctly here. There's no problem. Here, this is the number option converted to integer. And first we check, we compare with 1. If it's not 1, then we go over here. If it's 1, that means we go over here. Obviously, 1 was the option to play the game. So this is basically the logic to play the game. You can see that it's just a bunch of a lot of code here, but it's all linear and there's no paths to speak of, right? So it looks like we just have a bunch of printf stuff. We have this stuff, which is rather suspicious, but if you look at it, it's just ASCII. We're moving it to a certain location here, RBP plus test. And if we look into this a little bit more, we can see that what's happening is this is just a string copy of a hard-coded literal, right? These are just moving these guys together. Then we have an actual call to string cat with source here, and source was read into here whenever we enter the name. So let's go ahead and just call this name. Okay, and best we can just call this buffer. It's just something that's probably going to be printed somewhere, and we can see indeed there's a printf. Now you'll notice that we are concatenating the name to our buffer. Let me see, where is that? Yes, right here. So we're calling string cat on buffer with name. Name is something in particular that we control, right? It's something that we get to enter. So notice there is a format string problem if we directly print this buffer, which it looks like we do. So that is something to pay attention to. So, okay, that's good. We do notice there's a call here to a subroutine, and this looks like one of the puzzles. So we can call this puzzle 1, and there are 2 others just like it, of course, in the main subroutine. What happens here is we get a bunch of prints. We get a print of 3 options, and then we have a fgets. Notice we get fgets 80 right, into src. src looks like a global variable actually. So let's just call this global buffer. And then we have a scanf for a string into S1. Notice that S1 is at RBP minus 8, so this is actually very bad because the string here can conceivably be up to hex 80 in length. So we scanf here, there's a potential of overflow. But we have a string compare. String compare between the string that was scanf'd, right, and a particular constant here, RA1, which is probably the answer, right? Now notice that if we scanf, we could potentially overwrite and exploit using ROP, but the problem is there's a string compare here, which means that we can't really pass the string compare if we do overflow, right? This is kind of a it's kind of a easily verifiable fact, right? If we somehow get the overflow, the string compare will fail and we will jump to this side. Notice that this side doesn't do anything interesting, it just prints incorrect and then exits 0, so there's no return, right? But if we do want to pass the string compare and end up here, then we can't actually overflow this stack frame of this function. That's an easily verifiable fact. And in a sense, this is kind of like acting like a cookie, right? It's like the string compare of this value that's right below the save base pointer and return address. It's essentially acting like a cookie. Except this is a cookie that we know is just preventing us, right, from returning to stuff that we overwrite. Right. So that is essentially the puzzle. If we look down here, there are similar calls here. For example, there's a puzzle 2, and down here should be a puzzle 3. And at the bottom here, if everything is correct, then we get that message that we saw. We defeated the Bogotron, blah, blah, blah. Okay. So this is the entire program, and now we have to figure out a way to actually get a shell from this. So the first thing we're going to do is see if there's anything in here that could help us get a shell very easily. Now, usually CTF challenges will have a small subroutine that I call the shell. In this case, actually, we do see a string BNSH and another string that we haven't seen yet. Maybe that's actually in the admin area. So let's see, compare EX with 2, jump commands right here. So this is what happens for admin. And, right, well, actually that doesn't happen because you see we're unauthorized no matter what, so that won't work. But we do see these two interesting strings. Let's go and jump to the process reference. And we end up here. So notice that this is unexplored, or this is explored, but it's not a procedure. We can make it such just by pressing P to make it a procedure. And we'll notice that this actually runs system BNSH. Another way to kind of do a quick check for this is just when you have your vulnerable program open in IDA, you can check the list of imported functions. In this case, we see that system is here. So it helps to look whenever there's a call to system. Now, to be honest, in most cases, you won't find something as simple as this, right? You usually have to go through a more tortuous route, right, to get the shell. But in this case, we have it. So let's call this shell. Okay, so that's our goal, is to jump to this function, right? We just have to jump to it. If we jump to it, then we automatically get the shell. But how do we do that, right? So notice that there is no pi in this program. And because of this fact, the address of the shell will be known. And in fact, it will be exactly what IDA tells you. It's 401.1c2. So all we have to do is overwrite something to jump to there. Well, how do we get something to overwrite? Right? We use format string. Format string will allow us to overwrite something. Now notice that for this name here, this is actually not a lot of space. It's only 16 characters. That's probably not enough for a reliable, well, actually it may be, right? But probably not, because that means we'll have to, like hex 10, right? We need at least 8 for one address. So we can probably only write to one address if we think about 64-bit format strings, right? Which means that we'll have to write this gigantic number somewhere, which is probably not going to happen. However, we might not need to overwrite the whole thing, and this is especially the case if a particular function doesn't actually get resolved with its libc address. So let me show you what I mean. If we go and look at what happens in exit, for example, we see that, yeah, it defines an offset to exit, which is external. However, if we go ahead and GDB this program, and let's just break, let's break arbitrarily, it doesn't really matter. So let's just break here. Run, and it doesn't note here. So now let's look at the global offset table entry for exit. So we're going to examine one quad word at 404068. And notice that it contains a reference to 4010v6. So notice here we have this PLT entry, the actual PLT, and it's at 4010v6. Let's actually try to jump here. And we'll notice that it's actually a reference here in the PLT, right here. So the PLT, right, it's in the text section. So you notice it starts with 401v6. But we just want to write the address 4011c2. So conceivably, if we can just write here, this lower quad word here, we can't just write one byte because we need to also change this bit or nibble here, but that's okay. So let's see if we can fit this into a format string that is only 16 bytes long. So obviously we'll need the address of the exit entry in the global offset table. So in this case, it is 4068. And what do we want to write? Right? We need to write 11c2. Oh, what happened? C2, which is 4546 characters. But notice here, whenever we call print def on our buffer, we have some stuff concatenated before we put the name. Right, so obviously the buffer here should be empty. The string length should return 0. And then we're copying these 8, right, 2 times, so that's 16. And then we have 20 here. This is a space, right? Oh, we want to So this is congratulations. You can see it in the Indianness here, but this is 16. This will be 17. So we'll have 17 that are already printed. So we just need 4529. So let's try something like this. 2% 4529 D 1, 2, 3, 4, 5, 6. Oh, okay. So that's a problem. This is already too long because we also need to do percent argument percent agent. So this will not work actually. Yeah, we can't fit this in 16 bytes. But that's not a problem because if you'll notice, after we concatenate the name, it also tells us what our winning move was. And this is also something that we enter. Right? So if we go back here, we'll notice there's a reference here to globe buffer, and there's a string cat. There's a string concatenate global buffer. Of course, there's a lot more text here. And yeah, so let's look back at the program here. It doesn't matter what we use for our name. We just need to know its length. But we'll see. Oh, actually, yeah. So we have 17 characters here. String cat 17 plus length of the name. And then here's 8, here's 8, here's 8, here's another 8. So 1, 2, 3, 4, 5, 6. That's 48, and then we have this. This is 52. So we have 52 plus 17, which is 69. And this is the length up here. Then we print this global buffer, or we string cat this global buffer. Okay. So if we just say our name is admin, this will bump us to 74. Right, so if we, let's just add 17 to get back to 102, minus 74, oops. And this is the number of characters we'll need to write. So again, our payload will be in this global buffer. Now, we also have to know where exactly this global buffer is located in the memory, in the stack of main. Right, so if we look, the buffer here is at some offset of RBP, it's RBP minus hex A0. But our SP, it's 10, 20. So RSP is E0. We're looking at a buffer, so we can think about it like this. Here, RSP, there are this is RSP, this is RSP plus 10, or RBP minus 0. So that's C0, B0, and here is E0. So here's our buffer. Now, notice that whenever we call printf, right, in x64, this will be the 6th argument, right, of the printf. Because we'll have the registers, 5 of those, and then this will be the 6th one, it's our RSP. So our buffer will be, let's see, 6th. This is 6th, this is 7, 8, 9, 10, 11. Buffer will stay. Okay. So now we buffer probably have something like percent, or actually we need to first have this check. Right, so it needs to be rook one, and since we're scanning up the string, we can put white space here, and it will be read into the memory, right? It will be read into global buffer, but it won't be scanned out. So we'll still pass this check if we have white space here. Okay. So if we go back to here, we'll notice that we have 74 characters before, which is, I want to say, almost like 76, but that will not work. Because we need at least 3 here. So let's just go to the next multiple of 8. So 74, 75, 76, 77, and we need 7 spaces. So this will align us now with a multiple of 8. Right? And here, actually, we won't even need that, I think. We don't need to align this way. We can do 74. Oh, there's actually a little bit more. 74, 75, 76, 77, 78. So it's not just 74. We need to subtract 4 more. So 4, 4, 6, 8. So we'll do something like this. Right, this will get the count correct, and then do percent something dollar sign each n. And something will reference our string. So if we look at the stack now, so this is aligned with a multiple of 4. This will align, this is a multiple of 8. Right, so 1, 2, 3, 4, 5, 6, 7, 8. Now we can insert our payload here. And oh, but the problem is this will probably be 2 characters. So, which should still be okay. We'll just have to see. So we just won't have the space here. So now we have to figure out what is the position of this, right? Like we said, there's 12 here is the beginning of the buffer, right? If we have 8 characters in the buffer, it's 13. But if we look here, so this is 75, this is 5. So this will be at an offset 7, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. oh my bad, no, 74, 75, 26. 76 over 8. Wait, what am I saying? What am I saying? 72. My bad. So, okay, let me think this. So 74. We're going to get to 80. 75, 76, 77, 78, 79, 80. But this will be in line with the multiple of 8. And 1, 2, 3, 4, 5, 6, 7, 8. Yeah, probably need more. 1, 2, 3, 4, 5, 6, 7, 8. So let me here. This right here. Off at 80. Yeah. And 1, 2, 3, 4, 5, 6, 7, 8. So it's here. It's 88. Okay. So offset 0 is the 12, right? We just divide by 8 and add 12. So 11 plus 12 is 23. So this would be argument number 23. So we're probably looking for argument 24. Right here should be 96. Right. So yeah, this would be argument 24, which we have here, and this should work. Okay, assuming our name is 5. So to test this out, this is what we're going to do. Let's GDB this again, but we're going to break here. Oops. And have 40186C is where I set the def. And just as a test, we're going to put something strange, or we can just put an arbitrary 8 characters here. So we're going to do A1. We're going to add 1 space. And let's do 4468. Let's just copy this. Okay. And let's do it. So now we're calling printf. Let's examine what RDI holds. This is the format string that we're looking at, and let's examine this in the X view, actually. Let's examine 100px here, and notice that the string starts here, and notice also that this xxx is located here. Should actually be 8 characters. But actually, let me do something. Examine 100px from RSP. Well, here is, remember, is argument 6, right? And here's 8, here's 10, and here's 12. Notice that that is exactly where the buffer starts. Right? This is where our string continues on here. 12, 14, 16, 18, 20, 22. and 24, which is exactly what this reference is here. So let's go ahead and just set the integer here, because we know we control it, right? We just can't enter it whenever we're running GDB. Let's set that to the address of exit at GOT. So if we, which I think, yeah, is this. And now let's examine here, and you'll notice that we have changed, oh, it should be long. A new line here, but so now it's here, and whenever we run printf now, we should write to that address. So let's take a step, and now let's examine the exit entry. So notice we have successfully overwritten it with the function that we want to call. So this works. Okay. Okay. So now let's write this up and see what happens. Okay. So notice that, yeah, we'll have to pack 64 to ensure that we don't write a new line. We can't just write partially. So let's make so because I don't have the actual server, right, it's probably not even running at this point. We're just going to exploit this locally. But that should be sufficient. And let's test this out and see what happens. Before we do that though, I want to explain to debug. And let's break at the same location, 401 ACs. And let's test it out. So so it's interesting. Oh, so if you're using WSL terminal and you're trying to debug, you'll notice that you'll get, ooh, what happened? Yeah, you'll get this kind of error message, but that's okay. All you have to do is echo 0 to your proxys kernel YAML trace scope file. So let's try that again. All right, and now let's continue. breakpoint here, on string, and okay, so notice that we have this. Let's continue. Ooh, okay, so let's see, we have a problem. Oh, interesting. So it looks like we were trying to move this 11C2, which by the way is the correct half word, into this address. Notice that the lowest double word is correct, but the higher double word is wrong. This is probably because on the stack, so this is still fine. The problem is on the stack, whenever we're overriding our string here, we overrode something that, well, when we did the string copy, right, there was something already here with this stack address. So this is going to be invalid. Thanks for us, because all we have to do is just move it to a new location. So we can add another we can't have 0 here though, because I think that would just terminate the string. Just trying to string tag. Yeah, let's just add some spaces. Okay, and we just have to update this now with 5. So let's try that again. Let's breakpoint and call ni. Now let's examine one string here. And notice that it got successfully overwritten to 4011C2. Now the exploit is actually very simple. We just have to get something wrong, actually. So let's just type anything here. And you'll notice that now when we call exit, right, basically what happened is in this puzzle 2, we entered something wrong here, so we took this path and we called this exit, which actually jumped to our shell function. And now we have a shell. So of course, okay, my, and so we do have a shell, and that's essentially the whole challenge. Exit here. Now we know the answer is king d2. Yeah, and let's just exit. Okay, so just a quick recap about this challenge. It's a format string vulnerability. There was a very special function here called hitShell that essentially just gives us the shell. So we just need to write that to a global offset table entry. In this case, we chose the exit global offset table entry because it contained an address, right, that was pointing in the text itself. Now notice this will not work, okay, if your address, well, it won't work in one step, right, if your address is not in the text itself. You'll have to write multiple times. This is, of course, not an issue. You'll just need to do it multiple times. And once you have that overwritten, you can just trigger the bug and get your shell. Okay, so that's pretty much it. I hope you enjoyed. I know this took a little while, but I'm basically walking through the entire thought process of, first of all, identifying the vulnerability, and then crafting an exploit that will allow us to get an arbitrary write, and then, of course, get a shell. Okay, I will see you in the next video.